We'll write the expression first from the equilibrium constants. We'll try to establish the relation between Kp and C. This is the pressure, this is the concentration. We'll explain the various factors that affects the equilibrium. We'll also classify acids and base based on the Arrhenius, Lowry and Lewis concepts. We'll classify acids and base as weak and strong in terms of their ionization constants. We'll explain the dependency of degree of ionization on the electrolytes. We'll describe the pH scale for representing hydrogen ion concentration. We'll also explain the ionization of water. We'll have some term called Kw and pKw of water. We'll explain that. We'll learn something called buffer solutions. And we'll also learn something called solubility product. These things we'll learn in this chapter. Before we study equilibrium, the question comes to our mind is, what is equilibrium? Just don't think from the chemistry perspective. Just think from the word equilibrium. What is equilibrium? So equilibrium is nothing but a system in which the competing influences are balanced. For example, if you see the balance, the weight balance we have, the weight or the force which this guy exerts, similar force this guy exerts. So there is a balance. If you see this seesaw which kids play in the playground, there's a balance. One kid will sit here, one kid will sit here. They'll do a balance and they'll play. That's balance. So if you see this guy, gymnastic guy doing some equilibrium activities here, I'm using the audience by standing in this position. In this position, he is totally in equilibrium. If you see this, a good example is the stones. There's so many stones, one on top of each, bigger stone here, smaller stone here. But if you see, they're standing erect because they are equilibrium. If you push a little bit from this side, it will fall down. So there are examples of equilibrium. One good example is also a pendulum, or you just tie a ball with a wire and then you keep it for some time. It will dangle like this, and then after some time it will take this stationary position, because at this position it is an equilibrium. The force which it extends here is similar to the force which extends here, and end of the day this is equilibrium. And as we told that the whole model, or the whole reason how this universe works, the chemistry works, is the equilibrium. Everybody wants to be stable in equilibrium. We have discussed all this thing in the chapter of atoms, matters, where we discussed how the atom behaves and why they behave like that, why they can react. So because everywhere they talk about stability, right, and equilibrium. Everybody wants to be happy in life. Everybody wants to be stable in life. Similarly, we have equilibrium concept in chemistry. But in chemistry, we have something different. We have something called dynamic equilibrium. It is not really equilibrium, it is dynamic equilibrium. So what is dynamic equilibrium? Dynamic equilibrium is a condition where the rate of forward reaction is equal to the rate of backward reaction. But end of the day, it will be equilibrium. But it is dynamic. That is the beautiful part of this equilibrium. It is dynamic in nature, but it is in equilibrium. I'll take some examples because the concept has to be cleared. The rock example I took is not a dynamic equilibrium. It is equilibrium, but it's not dynamic because everything is constant here, right? Nothing is changing. But we'll take it through some examples. Example, in this case, there's a tap here, and there are two taps. From one tap, you're putting in some water, and the other tap is taking out some water. But if you see, the volume of water is this much only. That is constant, but it is dynamic in nature, right? Because from here, some different water is coming. From here, some different water is going out. So it's dynamic, right? If you let's suppose from here, if you pour some blue water, and from here, I mean, let's suppose red water, and then you start pouring blue water, you will see the change in color, because from here gradually, the more red will come, and then the mix of red and blue will come, and finally you'll see that not much red, only blue will be coming here. But what I'm trying to say is, in this case, if you see, the volume of the water is constant, but it is dynamic. It is equilibrium, it's dynamic. Water is coming in, water is going out, but it is in equilibrium. Example of dynamic equilibrium. One more example can be, let's suppose this is a shopping mall, and this is my entry here. This is my entry, and this is my exit, let's suppose. And I assume that this is 4 p.m. evening time, and let's suppose 50 people are entering into this mall every minute, and 50 are coming out every minute. 50 are coming out every minute. So the rate at which the people are going inside the mall and the rate at which the people are coming out of the mall is same. So in that case, if you see at 4 p.m. the number of people in the mall will be same, but it will be dynamic, right? Because some 50 people will have left, some new 50 people came. It's all dynamic, but it is an equilibrium because the number of people in the mall at this point in time is same, correct? But it's dynamic. One more example can I take is, let's suppose there's a big city and there's a small village here. A lot of people travel from here to there for work, right? A lot of people from village travel to. This is the corporate life. A lot of offices there. This is a place where people stay. Let's suppose 50 people, or let's suppose 100 people. 100 people go from village to the big city, and another lot of 100 people come from main city to village, maybe to look after village administration. But if you see here, the number of people going in coming out is same. There's equilibrium, and let's suppose this happens every hour, 100 people go from here to here, every hour 100 people come from here to here. So end of the day, if you see, both are in equilibrium, but the people are changing, right? So it's dynamic equilibrium. One more good example can be a bus. For example, let's suppose the bus is filled. Let's suppose the bus has 50 seats, all are filled. In the first stop, five people boarded the bus and 5 people came down. So total is still 50. The next stop, again 6 people boarded the bus and 6 people came down. Again the number of people in the bus is again 50 itself. Again let's suppose next stop 8 people came and 8 people came down. So in this case, if you see every stop, the number of people is same in the bus, but the people are changing, right? It's dynamic. So it's an equilibrium, but it's dynamic equilibrium. If you talk about the equilibrium from the economics point of view, demand and supply, right? So you have a demand for something, it keeps changing, right? The supply also keeps changing. It's not that we have demand for, let's suppose, shoes. Let's talk about pencils. Pencils or pens. So pen. Let's talk about pen. So let's suppose there are 10 demands for 10 pens. There will be an immediate supply of 10 pens. Again, let's suppose there's a demand 20 pen today. Again, there will be immediate supply of 20 pens. So demand supply is matching. The more you demand and more the manufacturer will be producing that. So demand and supply is one example where overall it is an equilibrium, but if you talk about only demand or supply, they are dynamic. So we have something called dynamic equilibrium. These are examples in the real world situation. Let's take something from the kitchen. So in cooker, if you see, so we have this pressure cooker, and let's suppose you put some water here and you boil it. What happened? The water evaporates, right? The water evaporates and it reaches an equilibrium. Then what happens? The water evaporates and the same water comes and cools down. Water evaporates, cools down. There's a dynamic equilibrium here. We'll discuss more about this in the next few slides when we'll talk about the equilibrium in the water pressure and water vapors. But here also we have something called equilibrium, and it's dynamic in nature where the water keeps evaporating, water keeps condensing. So that is dynamic in nature. Similar to what we have, similar examples what we have shown in the real world, same thing in the pressure cooker. It's dynamic equilibrium. Now the question is, we know what is dynamic equilibrium. The question now is, why should we study dynamic equilibrium, right? So now the answer is, so if you see our body, so we have fixed percentage of carbon dioxide, oxygen, water in the body, and everything is under equilibrium. In fact, we have a fixed concentration of hydrogen ions also. So we talk about acidity of blood, we have fixed level. So all these things are example of dynamic equilibrium. If you want to study the human body properly, you should know equilibrium, because in our human body itself, we have a dynamic equilibrium playing a bigger role, where we maintain the concentration of oxygen, carbon dioxide, water and all in our blood. Also, if you see, the bigger reason why we study equilibrium is in industries we produce lime, produce ammonia, we use the Haber process for this. We'll discuss this also in the next two slides. Sulfuric acid, methanol, in all these preparations, dynamic equilibrium is involved. Without dynamic equilibrium, you can't do, because we'll show you the beauty of dynamic equilibrium, where we try to maximize the production of ammonia by learning the behavior of equilibrium and then tweaking those behaviors in our favor to produce the maximum of these outputs, right? So when we have scenarios where we know we have to produce some products from some chemical reactions, and we know that it may go through equilibrium, and if we know all the properties of equilibrium, how it behaves, we can tame the equilibrium to make sure that we get the maximum product. And same thing we'll do in ammonia. We'll first learn the equilibrium concepts and how equilibrium is attained, how to tweak the equilibrium, and how to make the reaction fast, and this kind of stuff. And then we use all those methods which we have learned to show the production of ammonia. It's a big thing actually, because this production of ammonia by Haber process, it feeds almost 33% of the population, because also urea and others fertilizers which you get is from this. So there's a huge impact for on these chemical process, because whatever we consume in our life, for example, we car or use any products, chemistry is involved. In chemistry is involved, chemical process is involved. In chemical process involved, equilibrium comes into picture. So to gain the maximum from the chemical process, it's good to learn the equilibrium so that we can tame the equilibrium to get the best results. Also, example of pressure cooker which I took in the last slide, you see there also the equilibrium is there. So even if you don't want to go, you say I don't want to be a chemist, I don't want to be a doctor, at least you should have some curiosity to know what is happening in pressure cooker, right? Why do you use pressure cooker at all? What will happen if you don't use pressure cooker? So because in pressure cooker there is equilibrium involved, and with that it helps to cook faster. So we'll study all these things in the equilibrium chapter. Let's take a simple observation around us which has a dynamic equilibrium concept into play. For example, this is my glass of water, plain water, and this I add, let's suppose 2 teaspoons of sugar, and I mix it. If you mix it, you'll find that some of the sugar is gone, but some of the sugar is still there. Even if you mix more sugar, it won't get dissolved. Only a certain amount of sugar gets dissolved in, let's suppose, 30 ml of water. Some ml of water, only a certain amount of sugar gets dissolved. What happened to the rest? Why you can't add more sugars? Why there is a limit to the number of sugar crystals we can add to the water? Because it has reached equilibrium. Even if you add more sugar, it won't get dissolved. As dynamic in nature, we can explain it. Don't just assume that these crystals you see are not dissolved, and the ones which you don't see are dissolved. Actually, using spectrometer and all these things, scientists have shown that these sugars, it keeps going in, and the new sugar from the syrup comes up. There's a dynamic thing happening here, as we have seen the example of bus and the mall, where